Welcome back to our third week in our course Analysis of a Complex Kind. This is the second lecture this week, and we'll discuss the Cauchy Riemann equations. These are equations that result from a function being complex differentiable. As a reminder, remember that a function f that is a complex function can be split up into its real part u and its imaginary part v. When we write z as x plus iy, then f of z becomes u of x and y plus iv of x and y, where now u and v are functions that spit out real numbers and take two real parameters x and y. Let's look at an example just to remember the setting. Suppose f of z is the function z squared. With z being x plus iy, that becomes x plus iy quantity squared. And if I multiply through, this is x squared plus 2xiy, I wrote that term back here, plus I squared y squared. But I squared y squared is minus y squared. And so it's purely real, and I wrote it here in the front. If I collect all the real terms, I get x squared minus y squared, so that's my u of xy. And if I collect all the purely imaginary terms, I get 2xy, which is v of xy. And so my function u of xy would be x squared minus y squared, and v of xy would be 2xy. For example, if z is the number 2 plus I could just calculate f of z by taking 2 plus I and squaring it, which is 4 plus 4i plus I squared. Since I squared is negative 1, this simplifies to 3 plus 4i. Alternatively, I could use my functions u and v to evaluate the function f. So writing z as x plus iy, 2 plus I means that x is 2 and y is 1, the number that I gets multiplied with here. And so u of x and y, and I plug in x equals 2 and y equals 1, so it's u of 2 and 1. And since the function u is x squared minus y squared, it takes the first parameter that's entered and squares it, and subtracts from that the second parameter squared, so 2 squared minus 1 squared, that's 4 minus 1, that's 3. And similarly, v of xy would be v of 2 and 1. And since v takes those two parameters, multiplies them, and multiplies the result by 2, I would get 2 times 1, which is 4. So f of 2 plus I can also be evaluated by taking u of 2 and 1 plus I times v of 2 and 1. U of 2 and 1 was 3, v of 2 and 1 was 4, so 3 plus 4i. And that is indeed the same result we obtained by just plugging in z into the function f. So these are two alternative ways of looking at the same function, and they'll become helpful when we want to look at the function u and the function v and their differentiability properties. What do we already know about the function z squared? Well, we know this function is differentiable everywhere in z. In fact, we found its derivative to be 2z for all z and c. Let's just start by looking at the function u of xy more carefully. Again, u of xy is simply x squared minus y squared. So for example, if we fix a variable y at a certain value, for example, y equals 3, then the function u only depends on x. Because u of xy is then u of x and 3, if we always plug in 3 for y, then the function u of x3 becomes x squared minus 9. This function only depends on x, because y is fixed. And therefore, we can differentiate this function with respect to x. There's no y in there. I can find the derivative as I do in calculus of the function x squared minus 9. The derivative of that function is 2x. We write du dx of x comma 3 is equal to 2x, that derivative we just found. This is a notation for that derivative. We write that du dx is called the partial derivative of u with respect to x, because there also would have been a choice of finding a derivative with respect to y. And to indicate that I had a choice, I use these funny curly d's. So it's a partial u with respect to partial x. That's what that's called. But all that means is we fix y at a certain value and find the derivative with respect to x. Another notation is to omit this partial u, partial x, and put a little x next to u. That also indicates I'm going to take the derivative with respect to x. So that was 2x. More generally, if I plug in a different value for y, for example 4, then u of x and 4 would be x squared minus 16. The derivative is still 2x. And you notice, no matter what value of y I plug in, as long as I fix it, the derivative of u with respect to x is going to be 2x. And so we write more generally du dx of x and y, or ux of x and y is 2x. And again, this is called the partial derivative of u with respect to x. We can do the same thing for the function v. V of xy is the function 2xy. So for example, again, if we fix y equals 3, v of x and 3, we plug in 3 for y, is 2 times x times 3, that's 6x. The derivative of this function with respect to x is 6. And so we would write dv dx of x and 3, or vx of x and 3 equals 6. More generally, if I have a different value for y, for example, y equals 4, then v of x and 4 would be 2 times x times 4, so that would be 8x. And so the derivative vx of x and 4 would be 8. If I have yet another value, let's try v of x and 5. V of x and 5 is 10x, so that derivative would be 10. So the derivative seems to depend on y. Even though we're fixing y, the x derivative depends on y. If we look at this function very carefully, v of x and y equals 2 times x times y. If you think about this abstractly and say to yourself, 2 is a constant, and I'm going to keep y constant as well. I'm not going to change it. I'm going to plug in a value. I just don't know which value that is. But if I fix these two numbers, then this is really equal to these two constants, 2y, and those are both constant, times x. And the only variable that really varies is x. The derivative of such a function with respect to x, how do you find the derivative? Well, constants go to the side. So I keep the 2y, and then differentiate x. But what is the derivative of x? It's 1. In other words, the derivative of this function is simply 2y. The x derivative of v is 2 times y. And that agrees with these results. What we got? 8 when y was equal to 4, 10 when y was equal to 5, 6 when y was equal to 3. So generally we have the x derivative of v is equal to 2 times y. This is called the partial derivative of v with respect to x. Obviously, we can do the same thing by fixing x and differentiating with respect to y. For example, when x is equal to 2, then u of xy is u of 2y, which is 4 minus y squared. And the derivative of 4 minus y squared with respect to y is minus 2y. This is the regular derivative from calculus. More generally, if I look at this function u of xy as a function of y, and x is something fixed, even though typically x is the variable that varies. If I now think in my head, this is a constant, and I find the derivative of this function. The derivative of a constant sitting there by itself is 0. The derivative of minus y squared, if y is the variable, that's minus 2y. So more generally, the partial derivative of u with respect to y at x and y is minus 2y. Look at the notation. It's very similar to the notation we looked at earlier, except the partial x in the denominator here was replaced with a partial y. Similarly, we put a little y next to u to indicate we're using the partial derivative of u with respect to y. You can use either of those notations. We'll mostly use the u sub y notation. I can do the same thing for v. Again, let's fix an x value, 2 in this example, and look at v of x and y. V of x and y is then 2 times y, so 4y. And the derivative of the function 4y with respect to y is equal to 4. So we would write dv dy of 2 and y, or v sub y of 2 and y equals 4. More generally, if I look at this function 2 times x times y, and x is fixed and y varies, then the function v of x and y could be written as 2x, these are my two constants, times y. So if I want to find the y derivative of this function, it's a constant times y. The derivative of a constant times y is simply the constant, 2x. So more generally, the partial derivative of v with respect to y is 2 times x. Let's summarize what we have found. We started with the function f of z equals z squared, which we broke up into a real part u and its imaginary part v. U was x squared minus y squared, v is 2xy. And then we found all kinds of derivatives. The derivative in the complex sense of f was 2z. And then we had these somewhat real types of derivatives, the partial derivatives. Ux is 2x, uy is minus 2y, vx was 2y, and vy was 2x. We noticed certain things. Ux is 2x. So is vy. So ux is equal to vy. We also notice vy is minus 2y, and vx is 2y. They seem to be opposites of each other. Uy is minus vx. And finally, we notice when you look at the derivative of f prime, that's 2 times z. We could write that as 2x plus I times 2y. 2x, that's my ux derivative. 2y, that's my vx derivative. So I could write this derivative f prime. I could put that together from ux plus ivx. We call that the fx derivative. Alternatively, I could also use uy and vy. Since ux is equal to vy, I could write this as vy plus I times, and now vx is equal to minus uy. And if I factor out an I, this becomes minus uy minus I vy. Because I times I is minus 1 together with this minus 1, that gives me just this vy. If I indeed factor out a minus I, as I did right here, I find that f prime is the same as minus I times uy plus I vy. That's the fy derivative. Taking all of f and taking the derivative of f simply with respect to y. So f prime is the same thing as taking fx, or minus I times fy. Was that coincidence? Was it just true for the function z squared? Let's look at another example. Let's look at the function f of z equals 2z cubed minus 4z plus 1. Again, we write z as x plus iy, and when we plug that in, we find 2 times x plus iy quantity cubed minus 4 times quantity x plus iy plus 1. Now we need to multiply this through, unfortunately, so it gets a little bit ugly. X plus iy quantity cubed is x cubed plus 3x squared iy plus 3x times iy squared, so I squared y squared, plus iy cubed, which is I cubed y cubed. Then we can subtract from that 4 times x plus iy, so 4x and 4iy, and then add the 1 in the end. Let's collect terms. We want to find the function u and the function v. U is all the real parts, and v consists of all the purely imaginary parts. So what's real? X cubed is real. With that 2 in front of it, that gives me a 2x cubed. X squared I1, that's not real. 3x I squared y squared. I squared is negative 1, so this is another real term. With a 2 in front of it, that becomes 6xy squared. And with a negative sign because of the I squared. I cubed is minus I, so that's imaginary. Minus 4x, it's right here. And then there's finally the 1, that's right here. So we've now collected all the real terms. The rest is imaginary terms. 3x squared iy goes under v. With a 2 in front of it, that becomes 6x squared y. I factor out the I. Then I have I cubed y cubed. I cubed is negative I. So this is negative y cubed. With a 2 in front of it, it's a negative 2y cubed. And finally, minus 4iy shows up as minus 4 in my function v. In other words, u of x and y is 2x cubed minus 6xy squared minus 4x plus 1, and v of x and y is 6x squared y minus 2y cubed minus 4y. Let's find again the x and the y derivatives of these functions. Remember, to find the x derivative of u, we pretend y is a constant, such as 4 or 16, just a constant. And we just take a derivative with respect to x, as we do in calculus. So the x derivative of u becomes 6x squared minus 6y squared. Y squared is a constant, so that goes to the side. The derivative of x is simply 1. Minus 4. The derivative of this constant 1, which has no x attached to it, is 0. So that gives us the x derivative of u. If we wanted to find the y derivative of u, we would have to keep x constant. Now, 2x cubed is a constant with no y attached to it. The derivative of such a constant is 0. The derivative of minus 6xy squared with respect to y is found by realizing minus 6x are constants that go to the side. Y squared is a function that varies depending on y. Its derivative is 2y times the constant. I find minus 12xy. Minus 4x doesn't depend on y, plus 1 doesn't depend on y. The derivatives of these terms are just 0. Similarly, I find the x derivative of v. X derivative of v, y is constant now, is 12xy. 2y cubed and 4y are constants that don't depend on x. Their derivatives are 0. The y derivative of v, 6x squared, is a constant multiplied by y, so the derivative of that is 6x squared. The derivative of 2y cubed is 6y. The derivative of 4y is 4. So I find all these derivatives. Let's see what happens. Let's look at ux and vy, and we realize, again, ux is equal to vy. Let's look at uy and compare that to vx. Again, they are opposites of each other. So again, ux is vy, and uy is minus vx. But this function was a whole lot more complicated than the previous example. So now we're starting to think maybe this was not coincidence. Indeed, it was not. Let's look at how this is all related to the derivative of f. Again, I wrote down ux, uy, vx, and vy for us to remember. Let's find f prime. F prime in the complex sense. We find the complex derivative of 2z cubed minus 4z plus 1. The derivative of 2z cubed is 6z squared. The derivative of minus 4z is minus 4. The derivative of 1 is just a constant 0. So the derivative of f is 6z squared minus 4. We plug in z being x plus iy. This becomes 6 times x plus iy quantity squared minus 4. If I multiply through, x plus iy quantity squared is x squared minus y squared plus 2ixy. 2ixy times 6 is where this 12ixy comes from, and here I wrote down the real part, which consists of 6x squared, if I multiply x squared by 6, minus 6y squared, again, the minus y squared times 6, and minus 4 coming from this 4 right here. But when I look at this carefully, I recognize that this real term here 6x squared minus 6y squared minus 4, that's ux. And this term, 12ixy, that's I times dx. In other words, f prime, again, is ux plus I times dx. Or again, I can also write as minus I times uy plus I dy. So again, f prime equals fx of z, or minus I times fy of c. So it's no longer a coincidence. Here's a theorem. Suppose f is broken up into u plus iv, and suppose it is differentiable at a point z0. Then these partial derivatives all exist at z0 and satisfy these equations, ux is vy and uy is minus vx. This is a consequence of being differentiable. These equations are called the Cauchy Riemann equations, the very famous equations named after Cauchy and Riemann. Also, f prime, if f is differentiable in the complex sense, can then be written as ux plus ivx, which is the x derivative of f at z0, or minus I times uy plus idy, which is minus I times the y derivative of f at z0. Again, what this theorem is saying that if a function is differentiable in the complex sense, then it must satisfy the Cauchy Riemann equations. It doesn't say that the Cauchy Riemann equations are satisfied for all functions, only for those that are differentiable in the complex sense. If you wanted to prove this theorem, which we're not going to do in this lecture, it would actually not be that hard. You'd look at the difference quotient, f of c0 plus h minus f of c0 over h. And the limit of this difference quotient must exist if f is differentiable at z0, and that's your assumption. The limit of the difference quotient existing as h goes to 0 means we can let h go to 0 whichever way we want to. In particular, we could look at h going to 0 along the real axis, and we could also look at h approaching 0 along the imaginary axis. We could also look at h going to 0 all kinds of other ways, but it's actually sufficient in this proof to look at these two directions. So you'd let h approach 0 along the real axis and then along the imaginary axis only. And both times, this limit must exist, and both times you must get the same limit, because the limit must exist and be the same no matter how h approaches the origin. But by looking at these two limits and realizing that they must be the same, the Cauchy Riemann equations follow once you recognize the partial derivatives in the expressions. Let's look at another example. Let's look at the function f of z, which is the conjugate of z. So x minus iy. Z is x plus iy, the conjugate of that is x minus iy. In other words, my function u, which is the real part, is just x, and my function v is minus y. It's very simple to find the x and the y derivatives. The x derivative of the function x is 1. The y derivative, well, this function doesn't even depend on y, so this is a completely constant function for all y is concerned, and so the y derivative is simply 0. For the function v, it doesn't depend on x, so the x derivative is 0, and the y derivative is simply negative 1. Now when you compare ux and vy, they're not the same. So the Cauchy Riemann equations are not satisfied. Uy and vx, indeed, are, opposites of each other. 0 is the same as minus 0. But ux is not equal to vy, while uy could be regarded as minus vx. And therefore, the function cannot be differentiable anywhere. We don't have to check if f of z plus h minus f of z over h exists in the limit. We know, since the Cauchy Riemann equations are not satisfied, this function cannot be differentiable. Because if it were differentiable, then we would know from the previous theorem that the Cauchy Riemann equations would have to be satisfied. Again, remember, if f is differentiable at a point z0, then the Cauchy Riemann equations must hold at that point. Now, is the reverse statement also true? Is it true that if at a point the Cauchy Riemann equations are satisfied, then that implies the function is differentiable at that point? The answer is almost. Here's a theorem. Suppose f is defined on a domain D in the complex plane. Again, a domain is simply an open connected set. Then f is analytic in that domain if and only if u and v have continuous first partial derivatives on D that satisfy the Cauchy Riemann equations. So this theorem says two things. It says if f is analytic, then u and v satisfy the Cauchy Riemann equations and have continuous first partial derivatives. It's kind of what we already knew. But it also says if u and v have continuous first partial derivatives, then f is analytic if these derivatives satisfy the Cauchy Riemann equations. Continuous is the important part here. The first partial derivatives, it's not enough for you to be able to define ux, uy, vx, vy. These are the first partial derivatives. They need to be continuous. If they're continuous and satisfy the Cauchy Riemann equations, then f is analytic. It's a very subtle point, and this would mostly not be important for us. But one can actually find counterexamples. One can find a function that has these first partial derivatives and they satisfy the Cauchy Riemann equations, yet the function is not differentiable. And the reason is that there is a point where these functions are not continuous. But for now, let's look at an example. Let's look at the function f of z equals e to the x cosine y plus I e to the x sine y. This is our regular exponential function from real value calculus, and cosine our regular cosine function, and sine is our regular sine function. In other words, the function u is the function e to the x times cosine y. U of x and y is e to the x cosine y, and v is the function e to the x sine y. I can again find the x derivative of u, the y derivative of u, the x derivative of v, and the y derivative of v. Let's start with the x derivative of u. In that case, cosine y is simply a constant that I multiply e to the x with. The constant goes to the side, and all I'm defining is the derivative of e to the x. But e to the x has this amazing property that its derivative is the function itself. In other words, the x derivative of u is the same as u, it's e to the x cosine y. If I wanted to find the y derivative of u, now e to the x is my constant, and I need to find the derivative of cosine y. The derivative of cosine y is minus sine y, so the derivative becomes minus e to the x sine y. Similarly, the x derivative of v is e to the x sine y, and the y derivative of v is e to the x cosine y. If I look at these functions, I realize ux is equal to vy, and uy is equal to negative vx. So the Cauchy Riemann equations are satisfied, and these are all products of continuous functions, so ux, uy, vx, and vy are continuous in C. Therefore, by the theorem, this function f is an analytic function in C. In fact, I make it an entire function because it's analytic in the entire complex plane. This function, f of z equals e to the x times cosine y plus I times e to the x sine y, is going to be our complex exponential function. We'll study it in the next lecture.